Hello, my name is Maimin Ibnat.
My name's Katie Caro.
And I'm Sophia Sim. Today we're going to be talking about Poisson's ratio and using DIC to do our experiment. The objective of this lab was to determine Poisson's ratio for different materials using digital image correlation, or known as DIC. Our materials that we used were aluminum, copper, and polymer. DIC is a non-contact analyzation tool for measuring strain and deformation, and Poisson's ratio, other denoted as V, is the ratio of lateral strain to longitudinal strain. It indicates how a material deforms under stress and can be found using that equation. To complete this experiment, we had some steps that we had to follow. First, we had to prepare our sample. To do this, we measured initial dimensions, including gauge length, gauge width, thickness, and luckily the samples were given to us already spec'd. For the camera and digital image correlation, we aligned the camera perpendicular to the sample, and we made sure that there is enough lighting and focus on the sample as well. When we started the testing for DIC, we apply a preload force using the tensile testing machine, and we captured images at 20 Hertz for 60 seconds while loading the sample. We analyzed the images in GOM correlate. The controlled variables is that we had an applied preload and we were testing only 3 materials.
This is a graph of our two aluminum samples. On the top, we have epsilon x, which is the strain in the lateral direction, and on the bottom we have epsilon y, which is a strain in the longitudinal direction. As we can see in both graphs for the aluminum samples, there seems to be a positive slope showing that there was showing that there's strain in both the x and y direction. Same thing for the copper. On top there's epsilon x and on the bottom there's epsilon y. For the copper, for the epsilon x, the results were fairly similar to the aluminum. There was a positive correlation in the x direction, meaning that the material extended or expanded in the x direction. However, for the copper, there seems to be a slight negative correlation in the y direction, showing that the material shrunk in the longitudinal direction. Out of the three materials, nylon was the most apparent in the epsilon x direction, so strain in the lateral direction. There is a very obvious positive slope showing that it extended that way. And in the epsilon y, meaning the strain in the y direction, there's a very obvious negative slope for the nylon, which showed that the longitudinal strain had the dog bone samples decrease in the y direction. The literature values that we collected from the internet for the three materials is 0.334 for aluminum, 0.355 for copper, and 0.39. These are the literature values for Poisson's ratio. Our experimental values were slightly different. We had 0.19 for aluminum, 0.72 for copper, and 0.24 for nylon. And our percent errors are listed below as well.
So we did have some minor discrepancies when taking the measurements of our samples. There was some imaging issues and alignment issues. Also with our aluminum, specifically the first one broke because we were too fast. And the second trial aluminum didn't have any change, so we had to redo it because we had placed it wrong in the machine. So we did think that the samples would stretch, and they did stretch a little bit, even though that they didn't stretch as we thought they would. The nylon was the one we thought would stretch the most, and it did. So for future work, we would have set up the camera just a little bit better and also spent more time on the correlate graphs rather than the slideshow and the presentation.
These are our references. These are the two websites we use to find the literature Poisson's value for our three materials.
Thank you for watching our presentation, and we hope that we helped you learn something.